Okay, here are our notes for the remainder of Chapter 14, starting with Section 14.6. We've been talking mainly about strong and weak acids and finding their pHs. Now we're going to go the other half of the coin and talk about bases. Just like you have strong acids and weak acids, you have strong bases and weak bases. Your strong bases are the hydroxides from the metals that are on the first two columns. So the alkali and the alkaline earth metals make strong bases because when they are the hydroxide of lithium, sodium, potassium, calcium, barium, strontium, they are going to fully dissociate in water to make the hydroxide ions. So they're going to be strong electrolytes or strong bases. And that's because they break up 100%. Now keep in mind, if you are an alkaline earth metal hydroxide, it's a double base. So instead, just like H2SO4 is a diprotic acid, calcium hydroxide gives you 2 OH minuses per mole or per formula unit. Barium hydroxide also, and strontium hydroxide. And because of solubility, your double bases, your ones from the alkaline earth metals, do have some issues with solubility. Some of them have lower solubilities, and so even though they are strong and they break up completely, they may reach a solubility limit at a pretty low concentration. Magnesium hydroxide has a really low solubility. In fact, it's known as milk of magnesia because the little white solid pieces floating around in the water will make it look milky. Milk of magnesia is actually a medicine used to neutralize acid in your stomach. It's an antacid. And for two reasons, it's a very good choice for this. The first reason is since it does have very low solubility, the concentration of OH minus is not going to be very large, and that means it's not going to burn your throat on the way down because bases do dissolve skin. So milk of magnesia is safe to drink and take as a medicine because it's not very soluble in water, so it doesn't make a very high concentration of hydroxide. The other reason why it makes a good antacid is that it is a double base. It will neutralize the acid in your stomach. The solid will dissolve in the acid and neutralize in your stomach, but it'll give you 2 hydroxides to neutralize 2 protons for every 1 magnesium hydroxide formula unit. Calcium hydroxide is another double base, sometimes known as slaked lime, meaning you have slaked calcium oxide with water to make calcium hydroxide. And slaked lime is used in smokestacks. It is sprayed as a liquid in smokestacks to neutralize the acids in the smoke and limit the amount of acid rain escaping from a smokestack. If you mix slaked lime or calcium hydroxide with soda ash or sodium carbonate, the soda lime process can be used to take calcium out of hard water and soften water with the soda lime process. pH of strong bases, it's a fairly straightforward process, just like finding the pH of a strong acid. You just base the concentration on the concentration of the strong base. So just to illustrate that, let's say we have some 5 times 10 minus 2 molar NaOH. Well, since NaOH is fully dissociated in water, we can conclude then that the OH minus molarity is also going to be 5 times 10 minus 2 molar. The Kw for this is 1 times 10 minus 14 equals H plus times OH minus. So if the OH minus is 5 times 10 minus 2, the H plus is 2 times 10 minus 13. Take the negative log of that to get the pH. You've got a pH of 12.70. Notice above 7 because it is a base. Now, how would it change if, and I missed a parentheses here, how would it change if your base was calcium hydroxide? Well, if it's calcium hydroxide, the OH minus would be double since every calcium hydroxide gives 2 OH minuses. So instead of 5 times 10 minus 2, we would have 1 times 10 minus 1, and your pH would be 13. Now, a lot of proton acceptors don't contain hydroxide. Now these typically are going to be weak bases, and one set of these weak bases are the proton acceptors that are in the general family we would call the ammonia family. So this could be NH3 or similar molecules where maybe you've got carbon groups like methylamine or dimethylamine or trimethylamine or ethylamine stuck to the nitrogen. So they are all going to act similarly. Maybe they have a little different equilibrium constants, but they're all going to be weak acids, because in water they are going to accept a proton from water to generate the hydroxide ion. And so they raise the hydroxide ion concentration by taking H plus off of water, and it's always the nitrogen's lone pair, that or unshared pair, that ends up bonding to the hydrogen and pulling the hydrogen off of the water. So the general format with this would be that the base, maybe NH3 or could be methylamine, plus water makes BH plus OH minus. So the Kb, the equilibrium constant for the base, now again, we're just love it to put new suffixes on K. Kb is going to be BH plus times OH minus over B. So here are some Kb constants for a series of nitrogen-containing weak acids, or weak bases rather. Notice the Kb's do vary quite a bit depending on the type of weak base and its chemistry. Let's try one of these. Find the pH of a 15 molar, that's a very high concentration, 15 molar ammonia solution. And we know that the Kb for ammonia, NH3, is 1.8 times 10⁻⁵. So we always try to ask ourselves, what are our major species? We have water, we have ammonia. The ammonia is going to take H plus off of water and make hydroxide and produce the conjugate acid NH4 plus. NH4 plus the conjugate acid of NH3. So these are our mixture here, and I would say the pH is going to be dominated by that OH minus that you're going to make from the reaction between NH3 and water. So let's take a look at what that looks like as an ice table. NH3 plus water, B plus H2O, yields BH plus NH4 plus OH minus. And they told us in the problem we're starting with 15 molar NH3, 0 and 0 for ammonium. Don't care about the water. Water is a liquid, not an ion. Change, minus X, plus X, and plus X. So 15 minus X for the equilibrium for ammonia, X and X for the ammonium and the hydroxide. So this all looks familiar, looks like a nice table for an acid. Kb instead of Ka, but it's still worked out the same way. 1.8 times 10⁻⁵ equals x squared over 15 minus x. Drop the minus x, x squared over 15. Multiply both sides by 15, take the square root. I get x equals 0.016 molar. Now in this case, x is not the H plus, it is the OH minus. So I'm not solving for pH here, I'm solving for pOH. The negative log of 0.016 is 1.80. Subtract from 14, pH is 12.20. So the extra little step at the end there is you find the pOH, then you find the pH. Okay. Take a break from bases for a little bit here and talk about polyprotic acids. Polyprotic acids have more than one ionization step. Unless they're H2SO4, the ionization steps are all weak. So you're going to have more than one ionization equilibrium occurring simultaneously. For example, carbonic acid, the acid in sodas, has the first ionization step making H plus plus HCO3 minus, and that has a K of 4.2 times 10⁻⁷. The second ionization step is HCO3 minus, makes H plus plus carbonate, and that's the second ionization step with a 4.8 times 10⁻11 K value. So notice the K is quite a bit smaller for the second step. So if you take one H off of an acid, the second H always comes off more reluctantly. We see this also with the triprotic acid, phosphoric acid. H3PO4 making H2PO4 minus plus hydronium. That's K value is 7.1 times 10 minus 3. When you take the H2PO4 minus and take a proton off, it's 6.3 times 10 minus 8. Taking the proton off of HPO4 minus 2 is 7.1 times 10 minus 13. So this would be the 3 steps you would do to take all 3 protons off of H3PO4. And these are the K equilibria values, equilibrium constant values for each step. So notice the largest K is definitely the first step, and then the second step is quite a bit smaller, and the third step is really small. So comparing acid strengths, I would say H3PO4 donates protons to a lot higher degree than H2PO4 minus, which donates protons to a higher degree than HPO4 minus 2. So here's a chart showing, we call it Ka1, Ka2, Ka3 for various polyprotic acids. And it gives some numbers you could use in some math problems. So how would we analyze something like this? Well, you might have to do multiple ice tables, one for each ionization. Let's say we have some 5 molar phosphoric acid, and we want to know how much H3PO4, how much H2PO4 minus, how much HPO4 minus 2, and how much phosphate. And we also want to know how much H plus, because we have to find the pH. So they want 5 pieces of information out of us on this. So we're going to start with the first ionization, which we are going to say is the only important ionization for producing H plus. So we set it up as an ice table, 5, 0, 0, minus X plus X plus X, 5 minus X, X, and X. Set it equal to Ka, 1, the Ka for taking the first proton off, and do all of our assumptions and everything, and it all works out, and we get X equal 0.19. So X is 0.19, X is the H plus concentration, and X is also the H2PO4 minus concentration, and 5 minus X is the H3PO4 concentration. So we've got 3 out of 5 things calculated already if we convert our H plus concentration to pH, which is simply the negative log of 0.19, so it's 0.72. So we found the pH, 0.72. We found the H3PO4 concentration. After equilibrium, it's 5 minus X, so it's 5 minus 0.19, or about 4.8. We found that the H plus ion is 0.19, and we found that the H2PO4 minus ion is 0.19 molar. Now, to get the other 2 numbers we want, we're going to have to pull up the other 2 ice tables. So here would be the ice table for the second step. H2PO4 minus, which starts out as 0.19 from the other equilibria. And now we're making H plus HPO4 minus 2, but we're not calling H plus 0 because remember the first ionization step made 0.19 molar H plus. So it's starting out as 0.19 and 0 for HPO4 minus 2. We shift to the right just a tiny little bit. We get minus X plus X plus X. 0.19 minus X, 0.19 plus X, and X. Plug those into the Ka2 equilibrium expression. Ka2, remember, is 6.2 times 10 minus 8 for H2PO4 minus. Now we got X times 0.19 plus X over 0.19 minus X. So not only am I going to drop the minus X on bottom, I'm going to drop the plus X on top, because I'm going to assume for both of these that it's smaller than 0.19. And it turns out when I make that assumption, I get 6.2 times 10 minus 8 equals X times 0.19 over 0.19. Or in other words, X equals 6.2 times 10 minus 8 moles per liter of HPO4 minus 2, because that's what X is equal to in the ice table. That is quite a bit smaller than 0.19, so our assumption definitely holds by the 5% rule. Now we need one more number. We need the phosphate, PO4 minus 3 number. We're going to have to get that from Ka3. So now we set up the 6.2 times 10 minus 8 that we got from the previous problem for the HPO4 minus 2. We still plug in 0.19 for H plus, 0 for phosphate, minus x plus x plus x, 6.2 times 10 minus 8 minus x, 0.19 plus x, and x. And now we use the Ka for step 3, 4.8 times 10 minus 13 equals x times 0.19 plus x over 6.2 times 10 minus 8 minus x. Drop the plus x on top, drop the minus x on bottom, multiply the left side by 6.2 times 10 minus 8, divide the left side by 0.19, equals x, x equals 1.6 times 10 minus 19. So very, very tiny concentration of phosphate. But if you go back through those slides, you'll see that we did solve for everything they asked us to find. We found the pH, we found the concentration of H3PO4, we found the concentration of H2PO4 minus, we found HPO4 minus 2, and on this slide we found the PO4 minus 3. So those polyprotic acids, they can be a lot of ice tables to fully analyze every ion in the mixture. Now, let's get back to acid and base properties of things that are weak, but we're going to look at some places where you might not originally have thought to look. Sometimes acids and bases can hide as kind of disguised as other things. They can kind of be camouflaged and difficult to recognize. First of all, let's talk about what's not an acid base, and that would be a neutral salt. If you have the cation from a strong base and the anion from a strong acid, that cation and anion combination is not going to be acidic or basic. And that's because the stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. So an example of that would be salt water. If I have salt water, sodium chloride is not an acid and it's not a base. Because sodium comes from sodium hydroxide, a strong base. Chloride comes from hydrochloric acid, a strong acid. They neutralize completely, and you'd expect salt water to have a pH of 7. But there are salts that do make basic solutions, particularly if your solution has a cation, the positive ion, from a strong base, but your anion, your negative ion, is the conjugate base of a weak acid. So you would have to figure out an ice table for that, because the conjugate base of the weak acid is going to be basic, and that's going to need an equilibrium problem. Now, little trick. If you've got the conjugate base of a weak acid and you know the Ka of the weak acid, the conjugate base is mathematically related. Here's how. Let's take the generic weak acid HA. HA makes H plus A minus. It has a Ka that's equal to H plus times A minus over HA. Now let's take Kb. How could its conjugate base act as a base? Well, the A minus is a conjugate base of HA. A minus plus water makes HA plus OH minus. Kb would be HA times OH minus over A minus. Drop the water out. It's liquid. Now, I'm going to prove to you that Ka times Kb, the Ka of HA and the Kb of A minus, the conjugate base, multiply to give you Kw. So in other words, if you know the Ka, you can find the Kb. So here's our two equilibrium expressions. H plus times A minus over HA, that's Ka. HA times OH minus over A minus, that's Kb. Notice what happens. The A minuses cancel because A minus in the first expression is on top and A minus in the second expression is on bottom. The A minuses cancel. Not only that, the HAs cancel, and you end up with H plus times OH minus. H plus times OH minus is Kw. So we just showed that Ka times Kb equals Kw. Or, if you'd rather do it with the negative log of the numbers, pKa plus pKb equals pKw. And of course, Kw is 1 times 10 minus 14, or pKw is just 14. So let's look at how we could apply this information. Find the pH of 0.3 molar NaF, knowing that the Ka of HF is 7.2 times 10⁻⁴. Now NaF is not HF, but NaF does contain a neutral sodium and a conjugate base F- of HF. So how is the F- from the dissolved NaF going to affect the pH? Well, it's going to act as a base. What will its Kb be? What will the Kb be for F-? Well, remember, Ka times Kb equals Kw, so Kb is going to be Kw divided by Ka, or 1 times 10⁻14 divided by 7.2 times 10⁻⁴. So we're going to have a Kb value of 1.4 times 10 to the minus 11. Now if I write the equilibrium expression for F- acting with water to make HF and OH-, and then I make it an ice table, it's 0.3 for F-. I don't care about the water, 0 and 0 for the HF and the OH-, minus x plus x plus x, 0.3 minus x, x and x. Plug it into the Kb, and you get x squared over 0.30 minus x equals Kb, 1.4 times 10⁻11. Drop the minus x, solve for x, and I get OH- is 2 times 10⁻⁶. And that is small in comparison to 0.30, so it was a good approximation. OH- lets me find the pOH by taking its negative log, and then subtracting that from 14, I get the pH 8.31. So here's another place, another salt that can contain something that will affect pH. Let's say we have ammonium chloride, and we have 0.1 molar ammonium chloride. We want to know its pH. And we happen to, in the word problem, they happen to tell us that the Kb for ammonia is 1.8 times 10⁻⁵. Well, we don't have ammonia, we have ammonium, and we have chloride. But I don't care about the chloride because it's the conjugate base of a strong acid. Strong acids' conjugate bases are incredibly weak. But we have ammonium, the conjugate acid of the weak base ammonia, and it will have some acid properties. NH4+ will be acidic. Its Ka will be Kw divided by the Kb of ammonia. 1 times 10⁻14 divided by 1.8 times 10⁻⁵ is 5.6 times 10⁻10. That means I can set up an acid equilibrium problem with the weak acid NH4+. 0.1, 0, 0, minus x plus x plus x, 0.1 minus x, x and x. 5.6 times 10⁻10 equals x squared over 0.1. X equals H plus, which is 7.5 times 10⁻⁶. So the pH is 5.13. So in fact, the 0.1 molar NH4+ did make it slightly acidic. pH equals 5.13. Another place that acids can hide is in these metal ions that form these hydrated complexes with water and then are able to lose H+. So we talked about that some in class, how the aluminum +3 ion, say you have 0.01 molar aluminum chloride, you have to catch on to the fact that, oh, that's going to make aluminum +3 ion. Aluminum +3 ion is going to surround itself with waters, and then it's going to weaken the bond between the H and O in water, which is going to let it make H+. So this would be what the Ka is for aluminum hydrated 6 times, and this would be its ionization to make H+. And you do your ice table, use your Ka, you solve for X, and you get H+ as 3.7 times 10⁻⁴, or a pH of 3.43. So aluminum metal in water does have acidic pH. Okay, section 14.9 is back more to the theory, and we're looking at what are the factors that make one acid strong and another acid weak. Well, the structure of the molecule is going to affect the strength of the acid. When your H, that's the labile proton, the H that can come off into the water to make H+, When it's bonded to the molecule with a weak attraction, it's going to be easier to take it off and make the acid. So the weaker the bond, the stronger the acid. Also, the more polar the bond between the H and the molecule or the atom that it's attached to in the molecule, usually oxygen or maybe chlorine or something, the more polar that bond, the stronger the water can pull on it, so the stronger the acid as well. So you have two things here. The more polar the bond, the stronger the acid. The weaker the bond, the stronger the acid. So we have to consider both, because if you just look at one or the other, you can get fooled. If we take a look at HF, HCl, HBr, and HI, we might think, since HF is more polar than HCl, HBr, and HI, that HF will be a stronger acid. However, we'd come to the wrong conclusion, because generally we think of HCl, HBr, and HI as all strong, but we've seen problems where HF is a weak acid. So why would that be? And it's because even though the HF bond is polar, the HF bond is also an extremely strong single bond, and that's why water is not capable of pulling it apart completely, 100% of the molecules. When you have your oxyacids, your oxygen is going to be attached to elements like sulfur, nitrogen, phosphorus. The more electronegative the elements that are attached to the oxygen, and the more atoms that are electronegative attached to the oxygen, the more polar the bond's going to be and the stronger the acid's going to be. If I take a look at HOCl, HOBr, HOI, and then HOCH3, we have electronegativities. Cl is 3.0, Br is 2.8, I is 2.5, and carbon is 2.3. When we compare the Kas, notice the Ka keeps getting smaller and smaller due to the decrease in the polarity of the HO bond due to the decrease in electronegativity of the atom attached to the oxygen. Here we see that piling on with more and more and more other electronegative atoms onto the molecule continues to weaken the OH bond and polarize the OH bond and make the Ka larger. So we see that HClO is weaker than HClO2. That extra O brings another electronegative element in to help pull electrons away from the OH bond. Bring in 3 O's in, HClO3, now we're getting even larger. HClO4 is even larger. And so the more oxygens usually in an oxyacid, the stronger the acid, and the more electronegative the other element is, like sulfur, nitrogen, oxygen, or sulfur, nitrogen, chlorine, the stronger the acid. Another one where structure makes a difference is this idea of these hydrated metal ions. Aluminum is acidic, iron +3 is acidic. So the acidity of a metal ion in water depends on two things. The smaller the radius, the stronger the bond between the positive ion and the water, the weaker the bond between the O and the H, and the more polar it is and the easier it is to pull off and make an acid, H+. And also the greater the charge. So aluminum's got a full +3, so it's going to be more acidic than, say, a magnesium with only a +2. So it all has to do with just how strongly can we suck electrons or pull electrons off of the water molecule that's hydrating the metal ion. Another place where acids and bases can sneak up on you is in the form of metal and nonmetal oxides. When added to water, they produce acids and bases. So a nonmetal oxide, such as sulfur trioxide, when it dissolves in water, makes sulfur, I messed up, it's H2SO4, not H2SO3, sulfuric acid. You can tell I didn't balance the equation properly. SO3 plus water would be H2SO4, sulfuric acid. So burning sulfur will hurt your nasal passages and your throat, because smelling that sulfur trioxide means when it gets in your nasal passages and dissolves in the water, it's going to make an acid, and that's going to burn your throat or burn your nose. Metal oxides, on the other hand, are basic. So something like calcium oxide, when you slake it with water, makes calcium hydroxide a base. Getting close to the end here, the Lewis acid-base model. This is the third of the three acid-base models that are covered in Chapter 14. We started with the Chem 1 level, Arrhenius. Acids are H plus producers and bases are OH minus producers. We expanded to the Bronsted-Lowry definition, meaning acids are anything that can donate protons, bases can accept protons. Now we're looking maybe from the other perspective and saying, well, actually a Lewis acid is more not so much as a proton donor as an electron pair acceptor, and bases are electron pair donors. Now, that's not contradictory to the Arrhenius and the Bronsted-Lowry definition. It's just a variation on it that focuses on the pair of electrons that make the single bond when you do acid-base chemistry. So let me illustrate this. By the way, just to let you know, AP prefers Bronsted-Lowry model. So that's the one we spent the most time on in this chapter, is the Bronsted-Lowry model. But I did want you to be aware of the Lewis acid and base model. If we think about the reaction between NH3 to gain a proton and form NH4+, another way of looking at it is that the nitrogen's two electrons there, that unshared pair, is being donated to make a bond to the H+. So in that sense, the NH3 is an electron pair donor, the H+ is an electron pair acceptor. And so the NH3 is a base, the H+ is an acid. Similarly, let's say that we are neutralizing an acid and base to make water. The H+ is going to bond to the oxygen on OH- using an electron pair. So the OH- is donating electron pair to make a bond to H+ and form water. So the Lewis acid is H+, the Lewis base is OH-. Now here's a case where you would not think of it to be an acid-base reaction because there's no exchange of a proton. NH3 has an unshared pair. BF3 is octet deficient. Remember, BF3 has 3 single bonds to F, but it just doesn't have 8 electrons. However, if you react NH3 to BF3, you can make a single bond using the unshared pair from nitrogen, and now the boron does have an octet. But in the process of doing that, nitrogen was donating an electron pair and boron was accepting an electron pair. So in this particular model, NH3 is acting as a base, BF3 is acting as a Lewis acid. So this would not be an example of an acid-base reaction except in the Lewis definition. Finally, we look at the aluminum ion bonding to waters. See, the aluminum ion is going to single bond to the waters using the unshared pairs on the waters. So in that case, aluminum plus 3 is going to act as a Lewis acid to accept electron pairs. Water is going to act as an electron pair donor, a base. So we've gotten through chapter 14. Just to remind ourselves, when we're solving acid-base problems, we want to ask ourselves, what are the major species present? Is it aluminum plus 3, which can act as an acid? Is it NH4 plus, the conjugate acid of ammonia? Is it HCl, a strong acid? What are the major species present, and do any of them react in such a way that it goes to completion? If it does, we need to do that first and then look at what's left. What is the equilibrium dominating the solution? That would be another question to consider. Let the problem guide you. Read the problem carefully, see what's available. Ask yourself, have I seen one like this before? Can I use the same approach on it, or is this unique, and do I need to come up with a new approach to solve it? So let the problem guide you, be patient, and I would probably add, ask Mr. Koker questions, because he's seen a lot of these problems before over his 34 years of teaching, and he can probably help you see into the problem what you need to be focused on and get you to the right answer. Okay, so thank you everybody for your attention on this. This is the end of the Chapter 14 notes.